Hello students and welcome to the virtual science classroom again. Today we're going to talk about chemistry, and more specifically we're going to review a whole bunch of stuff that you would have learned in previous science classes. So we're looking at stuff you learned in Science 8 and Science 9, and we're just going to add a little bit of extra that you may or may not have covered last year. So today is a kind of a review lesson. Might be a little bit on the longer side. Please feel free to pause and rewind the video as much as you need to in order to go over the stuff. Okay, so there are notes available that go alongside this lesson that you're more than welcome to use along with me. So the first part, first of all, what is chemistry? A lot of people think chemistry is the study of chemicals, and they're not wrong. It's actually the study of matter. But if you subscribe to Walter White's definition from the first episode, chemistry is the study of change. And I really like this definition because it's really true. We're studying the change in matter or in the chemicals and what they do when they react with each other. So what is an element? An element is matter composed of one type of atom. Okay. All matter is made up of atoms. So atoms are the smallest piece of matter that exists with the same kind of properties. They are indivisible. Well, this is Dalton's theory that they were indivisible. We have since been able to split an atom, hello atomic bomb. But at the time, Dalton came up with that they're indivisible and indestructible. And we have since proven we have gone beyond that, but that is not a natural thing that necessarily occurs without help. So all atoms of a given element are identical. In mass and properties, so they have the same number of protons, neutrons, and electrons. Compounds are formed by a combination of two or more different kinds or different types of atoms. Yes, my writing is on par with how it normally is. And a chemical reaction is actually just a rearrangement of these atoms. And that's actually, this last one is what Science 10 really focuses on, is how they rearrange, right? So just to review, an atom is the smallest piece of matter that still has the same properties of the element. Okay, so within an atom, there are 3 subatomic particles. Actually, a few more, but the 3 main ones. So the protons are what have a positive charge. They exist inside the nucleus. So there's actually a table that summarizes this. They're inside the nucleus, and they have a relative mass of 1836. We'll talk about that relative mass in a second. Neutrons have no charge, but they're these big, bulky particles that also exist in the nucleus. So they have a relative mass of 1837. And as you can see, these two are very similar. Okay. An electron has an equal but opposite charge to a proton. So even though it's significantly smaller, it has a negative charge, and the electrons are flying around outside the nucleus, or not inside with the nucleus. So what we do, instead of having the relative mass equal these large numbers, we just say that a proton equals 1 atomic mass unit, and a neutron equals 1 atomic mass unit, and an electron has no mass in relation to the other two. Technically, it does have a mass. It's just 0.0001 of that mass and is insignificant and gets rounded off in any of the calculations. So we have this periodic table of elements that has all the elements placed on it in a way that makes a lot of sense, and we're going to talk about that soon. And this table of elements will give us information about each of the different types of element that exists. And remember, the atom is what makes up the elements, and we can get a lot of information from it. We're going to specifically look at carbon in the next section. So here it is on the periodic table of elements. It's to the right of this lovely staircase, which means that it is a non-metal, and it has a whole bunch of numbers on it. So we're going to talk about what those numbers are and what they mean and how we can pull the numbers off the periodic table and how we can use that to figure out what the basic atom of a carbon element looks like. So these are going to be your ionic charges. They were not on the periodic table for carbon, but if they were, they would say this. This is the atomic number at the very top. This is the symbol. So we represent carbon with the symbol capital C. The name of C is carbon, so there's the name. This has to do with quantum mechanics, which you will learn about in Chemistry 11 if this subject interests you. And this here is the average atomic mass. So there's actually carbon, elements of carbon that exist out there that have slightly different masses because they have slightly different numbers of neutrons. And we call these different forms of carbon isotopes. And normally we would learn about them in Science 10, but right now we're not. But just know that they take the relative abundance or the relative amount of the different isotopes for carbon that exist, and they calculate what the average mass is. So this number is actually an average, and that's going to come into, it's going to be important when we go to use it to figure out how many subatomic particles there are. Okay, so for an atom has no charge. It has not gained or lost any electrons, so we can pull the information directly off the table, the periodic table of elements. The number of protons is going to be equal to the atomic number. So that means the number of protons carbon has is 6. Because it is neutral, meaning it has no charge, it means it has the same amount of electrons. Because if you have 6 positive things and there's overall no charge, you need to have 6 of the equal but opposite charge to cancel them out. Okay, so that means you're going to have 6 electrons because the number of electrons will equal the number of protons. I'm just going to use a P here to represent protons. Okay. The number of neutrons is, you're going to use the mass to figure that out. So the mass of the element is all the protons and all the neutrons added up. If you're given a mass, you are going to use that mass and you are going to subtract the number of protons. Okay. But if you're not given a specific mass for a specific element or atom, you're going to use the average atomic mass. But it's an average, so it's got decimals. So you need to round it to the nearest whole number. So 12.011 is closer to 12 than it is to 13. So you're going to take 12. I don't know what happened there. You're going to take 12, which is the rounded mass, and you're going to subtract the number of protons, which was 6. So the number of neutrons in this case for carbon is also 6. Okay. Now for an ion is the exact same thing, except for it has lost or gained electrons. Okay, so that means the protons and the neutrons have to be the same. They haven't changed. The only thing that changes with an ion is the number of electrons it has. If it gains electrons, it's gaining more negative particles, so it becomes more negative. If it loses electrons, it loses all that negativity and it becomes more positive. So to find your number of electrons, you're going to take your number of protons and you're going to subtract your charge, including your sign. So let's say the ion was +4, okay? We would take 6 and we would subtract +4. And the number of electrons that C4 plus would have is it would have 2 electrons. If we did C4 negative, meaning it has a 4 negative charge, we would take the number of protons, which is 6, and we would subtract the charge, which is -4. 6 minus -4 is the same thing as 6 plus 4, which means it will have 10 electrons. Okay. So to summarize, the number of protons will equal your atomic number. Your number of electrons will equal your number of protons minus your charge. So if it's a neutral atom, your charge is 0, which means your number of electrons will equal your number of protons minus 0, which means your number of electrons will equal your number of protons. And your number of neutrons is your mass minus your number of protons. So that's how we find our important numbers. Okay. So the reason we want to find these numbers is because we use them to construct our Bohr diagrams. Okay. So our Bohr diagrams are what you have learned about how to represent what an atom looks like. The Bohr diagrams are diagrams that show how many electrons are in each shell surrounding the nucleus. So the first shell right around the nucleus can only fit 2 electrons. The next shell can only fit 8. And the next shell after that can only fit 8. And the next shell after that is kind of like what we call the overflow shell for right now, because we're only focusing on the first 20 elements on the periodic table of elements. When you get to Chem 11, you're going to learn that there's actually a lot more than just these shells. There's all these like special shaped shells, and if that interests you, it's quantum mechanics, and it's very, very fascinating. So, but for right now, all you need to remember is 2, 8, and 8. And the reason that they have specific amounts that can fit in there have to do with this quantum mechanics that you'll learn later, but also because electrons hate one another. Like charges repel. But the electrons also are attracted to their opposites, which are the protons. So you have this super positive proton rich nucleus of the atom, and you have these electrons that really want to be close to that nucleus, but also want to be as far away from each other as possible. And it's because of that dynamic that we have these certain shells and spaces where electrons exist. Okay, so to draw it, we have to know how many protons and neutrons there are, and they go in the nucleus, so that's how we draw it. And then we're going to fill the electrons with the closest shell first. We're going to fill it up first before we go to the next one. And the idea is, like, if you're in another analogy for that is if you were like going to go to the mall and there's a parking spot right beside the main doors, and then there's a parking spot in the overflow parking way out there, where are you most likely going to park? You're going to park in the closest parking spot because you want to be as close to the door as possible. And that's the same thing with electrons. They want to be as close to that nucleus as possible. It's only when those shells, or in my parking spot analogy, the parking spots are filled up, that they start to move further and further away. So we have 6 electrons in total. The first 2 go in the first shell, and you can either write it like that, or you can write it like this as a pair. Right? So that's 2. That means I have 4 left. So to fill up the next shell, we always write it in kind of points of a compass. So we go 1, 2, 3, 4. Now we only have 4 to do, and we are now done. But let's just look at if it was a different atom. Let's just say there was 2 more that we would have to do. There was 2 more electrons we would have to write. We would then pair up the 5 and 6 into pairs. We don't just spread them out equally in the outer shell. You might have been taught that in Science 9. It's not wrong. It's just that it helps you if you're moving to Chem 11 to think about the electrons pairing up after they've filled the basic positions around the electron shell. So this one doesn't have 6, it only has 4 in the outer shell, so that's what the atom for carbon looks like. Now, you might have been taught a condensed version. So the condensed version is you do the symbol, and then you say, you draw it like this, and then you would say, oh, there's 2 electrons in the first shell, and there's 4 electrons, that's a 4, not a 9, in the next shell. And you would have written it like that. Okay. Another condensed version is you actually just draw half of what I just did there, where you say P6, N6, you draw half the nucleus, you draw half the first shell and say there's 2 electrons there, and you draw the half of the second shell and draw it there. Either way is fine. We're actually going to move past Bohr diagrams and use Lewis diagrams to focus on the next portion of this lesson. So in order to, I just want to summarize something first before we move to the next part, and that's the periodic table of elements. It's also known as the periodic table or the table of elements or the periodic table of elements. And what it does, it represents patterns related to the number of protons in the atoms of the elements. This pattern helps explain how elements behave during chemical change. And it also is very convenient for helping us determine how many electrons an atom has. I'm going to show you what I mean. So if you recall, we just went over this like 2 seconds ago, the Bohr diagram. We know that they fill up in a certain way. If you look at the periodic table, it's actually arranged very convenient. So here it is, and it's been drawn, and you can't see me pointing, but it's been drawn with the Bohr diagrams of the first 20 elements. You'll notice that it's actually taken this whole section out right here, and it's cut it out because we're not going to focus on that. Those ones have some special shells that you learn about later on if you so choose to. So we're just focused on the first 20. So if you notice, each row or period has the same number of shells. So the first row has 1 shell. The second row has 2 shells. The third row has 3 shells. And the fourth row has 4 shells. Now, if you look very closely at this diagram, now for the columns, what do they have in common? And if you look very carefully, you'll notice that they all have the same number of electrons in the very outermost shell. So if it's in the first column, there's 1 electron in the outer shell. If it's in the second column, there's 2 electrons in the outer shell. The third column has 3, the fourth has 4, the fifth has 5, the sixth has 6, the seventh has 7, and the 8th row is a little special. It has 8 if it's these ones, and helium just has 2, because remember, only 2 electrons can fit in the very first shell, and helium only has 1 shell. So instead of saying 8 for that last column, it's, I think, better if you think of it just being full. It's got a full outer shell, okay? So that helps us figure out that information. So if I go back to that periodic table, and we remember that we're going to cut out that part that is, I highlighted in yellow. we count the columns 1, 2, skip a few, 3, 4, 5, 6, 7, and full. So in summary, the number of row it's in equals the number of shells, and the number column, so that's the up and down, column, I can spell, equals the number of, I'm going to use a word here, valence electrons. So valence electrons are the electrons in the outer shell. Now this is a very nice tidbit of information because it's only the electrons in the very outermost shell that are involved in bonding. And that's because all the other shells inside are full. And because they're full, they're content. They don't want to do anything. They're fine. So they don't react. And you'll see that with all the elements that are in the 8th column, that full shell column, are the noble gases. And noble gases are known for being very inactive. They don't do anything because they don't want to, because 1, they don't have conscious thought, but 2, because they have complete full shells. Okay. So we are going to focus on just the outer shell. And to do that, I'm going to introduce a new portion, or new thing, that may or may not be new to you, depending on who you had for Science 9. I'm going to talk about Lewis diagrams. And the reason why I'm going to talk about Lewis diagrams is they're very, very handy when we're talking about bonding. So instead of drawing 4 shells and having to figure out how many electrons are on all the inner shells, we can just focus on the electrons in the outer shell, which is what we need to do when we're talking about bonding. So Lewis diagrams were invented by a guy named Lewis, last name, invented a concise method showing bonding. Bonding between 2 or more atoms involve only the electrons in the outermost electron shell. These electrons are known as valence electrons. So Lewis diagrams show only the valence electrons, and this little E with the negative sign is my shorthand for electrons, and the chemical symbol. Okay. So how to draw it is you draw, if we're going to draw carbon, which we just did, you draw the symbol for carbon, which is C, and then you just draw the electrons in the outer shell. So for carbon, the atom, it had 4 electrons in its outer shell. So start in the north position, 1, 2, 3, 4. That is the Lewis diagram for carbon. Way faster than doing 6 protons, 6 neutrons. There's my nucleus. There's 2 here. 1, 2, 3, 4. And carbon's a small one. Imagine doing it for one of the bigger ones. It's a lot of time and it's tedious. Okay, got another 11. So the reason we're learning about that is because we're going to talk about bonding. The whole goal of today's lesson is that you're able to construct a formula for 2 ions reacting together. And in order to do that, we need to talk about the electrons in the outer shell, which is why we've talked about how to find the electrons in the outer shell and basic atomic structure. So if you recall, here is the Bohr diagrams for sodium and chlorine. Sodium has 1 electron in its outer shell. It's not a happy shell. And chlorine has 7 electrons in its outer shell. And it's not a happy shell either because they both want full shells. So what happens in an ionic relationship is sodium fully gives away its electron and chlorine fully takes it. An ionic compound is between a metal and a non-metal. So something from that left side of the periodic table with something from the right-hand side. Okay. So how we represent that in a Lewis diagram is much nicer than a Bohr diagram, in my opinion. So here's sodium with just the 1 electron in its outer shell. Here's chlorine with the 7 electrons in its outer shell. And we can see that it just goes right there. Okay. So sodium, after the reaction has occurred, this is the compound sodium chloride, which is salt, you'll notice that there's no electrons around sodium because that outer shell is now empty, and you'll see that chlorine now has a full outer shell. Now for sodium, we don't draw the fully inner shell that was already complete in the diagram because that complete inner shell was not involved in the bonding process. We should have the same amount of electrons in the final as we do before the reaction happened. So if we look at magnesium oxide, magnesium has 2 electrons in its outer shell, because if you look at magnesium, it's in the second column. And if you look at oxygen, it's here, and it's in the 1, 2, 3, 4, 5, 6th column. So that is why we see magnesium with 2 electrons drawn outside of it and oxygen with 6. Now oxygen, it's much easier for oxygen to gain 2 electrons than to find and rehome 6 electrons. So it's going to take electrons. And the metal magnesium is going to give its electrons. The metals are always form something called a cation, meaning they always become positive because they give their electrons. Nonmetals are negative. They will either take electrons if it's an ionic compound, or they will share electrons in a covalent compound, which we're not talking about at the moment. Okay, so this electron goes here, this electron goes here, and you end up with Mg, and we're going to draw it with no electrons because all the electrons in its outer shell are gone. It lost 2 electrons, so it becomes positive, more positive by 2. And we have oxygen that had its original 6 electrons, but gained 2 more. So it gained 2 more negative things, so becomes 2 negative. So this is why we're doing this, is that we need to be able to take our electrons, we should be able to take our ions or the charges of things and make a compound. So let's say we were going to say, hey, magnesium, and let's do nitrogen. Okay, so we want to form a compound, meaning something that contains more than 1 element, between magnesium and nitrogen. So the first thing we need to do is find out the charge of these things. So magnesium, I've already circled, is here. So if it forms a compound, it's got 2 electrons in the outer shell, so it will become 2 positive. And this is actually given to you in the upper right-hand corner, which I've already written all over, but that's where it is. And if you look up nitrogen, it's in the 1, 2, 3, 4, 5, 5th column, which means it has 5 valence electrons, which means it will want to gain 3 more to become fully filled with electrons at the end. And that's why it has a 3- charge, which again we can read off of the periodic table. So we have Mg2+ and sodium 3-. So the first thing you're going to do is write out the ions. Okay. Now I'm going to show you the fast way of doing this. I'm going to explain why it works in a second, but you're going to cross the numbers. Okay. So you're going to take the 2 and cross it over and down, and you're going to take this 3 and cross it over and down. Okay. So you're then going to write the subscripts. So subscripts means it's written smaller and below. So you're going to write Mg, And we always write our metal first and then our non-metal. Okay. So our metal is written first, Mg, so the one with the positive charge is written first, no matter what. And then we're gonna write the subscript 3, because that came from the nitrogen. Not 3 plus, not 3 minus, just 3. That means there's 3 magnesiums. And we write the next symbol for nitrogen, which is N. And then we write the subscript for nitrogen, which is 2. And then we reduce if needed. So right now it's saying for every 3 magnesiums, there's 2 nitrogens. It's a 3-to-2 ratio of magnesiums to nitrogens. If that was a fraction, we wouldn't be able to reduce it. So it just stays as Mg3N2. Okay. Now I'm going to draw why this is, why this works. And there's actually more than one way to explain this. But if you have Mg, which is 2 plus, and you have sodium, which is 3 minus, meaning it has 5 electrons, you're going to have Mg give away its 2 electrons. But this nitrogen is not happy yet still. So it needs another Mg to react with it. So that one goes here. So now this nitrogen is happy, and you can't see me pointing, but the nitrogen's happy, and the magnesium on the left is happy, but we have this electron that still needs to go somewhere. So then we go, okay, well, we must need another nitrogen. Like, you have to keep going until everyone's happy, right? So that magnesium is now happy because it's given its electron away. But as you see with nitrogen, the second nitrogen, it's not happy because it's not full. So it needs another magnesium. And then this magnesium gives its 2. Now, all 3 magnesiums are happy. They've all given away all their electrons, and both the nitrogens are happy because they've gained all their missing electrons. And now this is a happy compound. How many magnesiums were there? 3. How many nitrogens are there? 2. And that's how we get the compound, the chemical formula for magnesium nitride. Now, the other way you can do it is the mathematical way, which of course I love. And how you do that is you take the charge of magnesium, which is 2 plus, and you take the charge of sodium, which is 3 minus. You need a certain number of magnesium and a certain number of nitrogen, and they must equal the same number but opposite signs. So you have to look at the lowest common multiple of 2 and 3, which is 6. So you need to have a total of 6 positive charges and a total of 6 negative charges because a compound overall is neutral. So what number times 2 will give you 6? It's 3, which is why we have 3 magnesiums. And what times 3 will give you 6? The answer is 2. And that is why we have 2 nitrogens. So there's the diagrammatic way of understanding how a formula comes to be, or how we get this formula. There's the mathematical way, that's also that I just did to get the same thing. Or there's this way that I did right here, which is called the crossover method, which I have found most students prefer. Okay, so I want to do one more example. I'm going to do Mg 4 plus and oxygen 2 minus. Okay, so I'm going to cross the charges over for step 2, and then I'm going to rewrite the new subscript. So this is going to Mg2O4. Notice my subscripts do not have any plus or minus signs. And now I'm going to reduce as possible. If you have the fraction 2,4, could you simplify it? The answer is yes. So it will become Mg1O2. So 2 to 4 ratio is the same thing as a 1 to 2 ratio. Now technically, if there's no subscript written, it was technically a small little itty bitty 1. But chemists, like mathematicians, are super lazy. we don't write the number 1 if the symbol's there, because if it was 0, we wouldn't write it at all. And if it's more than 1, we write the number. So when it is 1, we get really lazy and we don't write it. Okay. All right, so to do the rest, we are going to look at non-binary polyatomic ions or ionic compounds. So this is actually the same thing that you would do. So I've given you a chart of polyatomic ions. Looks like this. All right, so these are negative ones, and this is the one positive one. So these act like nonmetals. And even though this one contains nonmetals, it acts like a metal, meaning that it's going to lose electrons. Okay. So how you handle them, though, is no different than how we just did the writing the formula. Okay. Because the polyatomic ion is polyatomic, meaning it has more than one type of atom, but it acts as if it's like its own thing. Okay. So an example is sodium sulfate. So sodium is Na+, and sulfate is SO4 2-. We just leave this and pretend nothing's happening with it. It's one whole concise unit. We don't touch it. We don't change that 4 in any way. We leave it as one concise unit. So we are going to cross over our charges. If there's no number there, it's a 1. So that's going to go down here. And we take this charge and take the number and bring it down. Step 3 is to rewrite it out with the subscript. So it's going to be Na2, and it's going to be SO4, and there's going to be one of them. So technically, we would write it like this. But again, lazy chemists, there's one of them, so we don't write it. So it just ends up being written like this. Okay. And we leave it. Can you simplify a 2-to-1 ratio? Remember, it's not 2-to-4, it's 2-to-1. Can we simplify that? No, so it just stays as Na2SO4. We do not simplify that 4 because SO4, this whole thing, is a polyatomic ion called sulfate, and it stays sulfate. It doesn't get broken up. Let's try another example. Ca2 plus and PO4 3-. Okay, so we cross over the charges. We rewrite them out. So how many calciums do we have? 3. How many PO4s do we have? 2. And can the 3-to-2 ratio be simplified? No. So this is our compound right here. And that's how you name or write the formula for an ionic compound that involves a polyatomic ion. Next, we're going to talk about is multivalent metals. And this one is really no different than step 1, but you have something like vanadium. So the only difference for this is if you look up vanadium, find my periodic table. If you look up vanadium, V, where is she? Having a moment, only because I'm on film. I would find it very fast otherwise. There's vanadium. If you look at vanadium, and you look in the upper right-hand corner, it has 5+ and 4+ as an option. So you don't know which type of vanadium is going to be in the compound unless it's been given to you. And here it's saying vanadium 4. So if you see Roman numerals, it means that there's more than one type of charge, and those Roman numerals tell you which charge is being used. So it's vanadium 4. And because it's a metal, it's 4+. Oxygen, if we go back to our periodic table, is right here, and the charge for oxygen is 2-. So now we're right back to where we were with step 1. We do crossover. So how many vanadiums are there? 2. How many oxygens are there for every 2 vanadiums? 4. We rewrite it out. And can we simplify the ratio 2 to 4? Yes, we can. It's a 1 to 2 because both these numbers are divisible by 2. So 2 divided by 2 is 1, which we didn't write because we're lazy chemists. And 4 divided by 2 is 2. All right, the last type is what we call a covalent compound. Covalent compound occurs between 2 non-metals, and it's when they share electrons. There is a way to draw them that's really fun to do with Lewis diagrams, but we're not going to cover that right now. But the great thing about covalent compounds is it tells you how many. You don't have to do any crossover method. You don't have to look up charges on the periodic table. It tells you with the name how many things are there. So for example, if we had carbon dioxide, we're dealing with carbon, which is C, and oxide, which is the converted form for the name oxygen. If there is no prefix, it means the prefix was a 1, or it was technically a mono. But for some reason, if it's a 1 for the first element, so monocarbon, we don't write it. If it's monoxide for the second thing, we still write it. It's just the way it is. All right, so how many carbons are there? There's 1. How many dioxides are there? Well, di is a way of saying 2. So there's 2 carbons. And again, because we're lazy chemists, we don't actually write that 1, so we write it as CO2. So there's no crossing over. There's no looking up the charge. You take the prefix, and that tells you exactly how many of the element it directly precedes that there is in the compound. So another example, let's do dinitrogen trioxide. So first step, write down the symbols, nitrogen and oxygen. Di is how we say 2. So there's not a highlighter, that's for sure. There is 2 nitrogens. And how many oxygens do we have? The prefix says tri, so that means there is 3 oxygens. So the chemical formula for dinitrogen trioxide is N2O3. How do you know what the prefixes are? This is actually given to you on an information table right here. So mono is 1, 2 is di, 3 is tri, tetra, penta, hexa, hepta, octa, nona, and deca with your polygons. Okay, I know this is a long video. We're going to do one last thing, and that's how we go in the reverse order. Okay, so going in the opposite order. Naming the compounds. So this is when you're given the formula and you need to know the name of it, and it helps to be able to go back and forth. So if you have sodium chloride, you name the metal first. So the name of this is sodium. And you name the nonmetal which is, in this case, chlorine. And you change the ending to an IDE ending, because chlorine is an element all by itself. Chloride is inside a compound. So you're going to take that ending, INE, and you're going to change it to IDE. So that's going to become sodium chloride. So okay. To name a non-binary ionic compound, this just means it's again, one of those ones with a special polyatomic ion. So that would be something like aluminum hydroxide. So when you see something like this, hopefully you notice that it's a metal, just like there was a metal here. But instead of it being with just one non-metal, so there's only one capital in that highlighted blue section, here there's more than one capital letter, which means there's more than one atom or element present. So more than one different type of element. So you're going to look at that list and find the name for that thing, the O and the H together, okay? And the O and the H together is hydroxide. So to name something that's with a hydroxide, you're still going to name the metal first. So Al, you look it up on the periodic table of elements, it's aluminum. It's right here, okay? So we just copy the name down, aluminum. We do not change the ending to a metal name ever. And then we name this thing, which we looked up on the forum, and it's hydroxide. Now, this is one of the only polyatomic ions that ends with IDE. The other one is cyanide. All other polyatomic ions end with things like sulfate and sulfite and phosphite. They end with ATEs and ITEs to kind of indicate that they're polyatomic ions. Hydroxide and cyanide are little tricksters that they look in their names, they look like they're non-metal, just one non-metal, but they're actually in a polyatomic ion. Okay. But their name didn't get changed, it's just directly read off of that form. So multivalent metals, remember multivalent metals, some metals can form more than one type of ion. We call these multivalent. That was vanadium from our previous example. When naming multivalent ions, you must indicate which charge of ion is present. And we use Roman numerals to do that. So step one is you're going to actually uncross. You're going to work backwards. This is the trickiest one because you have to figure out what charge was present. So you're going to uncross the charges. So that means vanadium was 2 plus and oxygen was 1 minus. But you're going to write them out like that. And then what you're going to do is you're going to actually verify, can oxygen have a 1 minus charge? And the answer is no. So vanadium, VO2, vanadium oxide actually got its subscripts reduced. And you have to figure out, well, what was the original charge? So you're going to figure out how did it go from 1 minus, or from 2 minus, sorry, to 1 minus in the compound. It got reduced. So you're going to work backwards. What times 1 will give you 2? And the answer is it was multiplied, you multiply by 2. So that means you have to take vanadium's charge and also multiply it by 2, which means it was vanadium 4 plus that was involved. And to double check, you should be able to go from V4 plus O2 minus, these two ions, and put them together like we did in the last section of notes, and you should be able to get VO2. Okay. So what charge was involved? The charge that was involved for vanadium was 4 plus. So we write the name for vanadium. We write the charge vanadium had as Roman numerals. Then we write the non-metal, which is oxygen, and we change the ending of oxygen to an IDE ending. And that's how we do a multivalent metal. So whenever you have an ionic compound like this, you need to look up the metal and make sure there's only one charge. If there's not one charge, you have to figure out what charge was present by doing all of this stuff. Feel free to pause the video and replay or try those instant practices before moving on to the next spot. All right, so covalent compounds are, remember, the ones that use the prefixes. So you don't have to find what charge was used. You just use the prefixes or use the number of the subscript number, sorry, to figure out what prefix is used. So let's do CS2 first. So we're going to, first of all, look up what is C. We look up C on the periodic table. It's carbon. Okay. How many carbons are there? There's technically one because no number was written. The prefix for one is mono. So technically this would be monocarbon, and I'm going to talk about why it's not that in a second. And now we're going to do the second one. So the second one is S2. How many S's are there? There's two. The prefix for two is di. So we look up, we give it di. We look up S, and it's sulfur. So we write disulfur, and sulfur in the States has an F, and sulfur in Canada has a PH. Either one is fine. Don't particularly have a preference. And just like with the other nonmetals in the ionic compounds, we change the ending to IDE. So we use the prefix to indicate how many there were. And we also change the ending of the second one to IDE. Now, just to add complexity, if it's mono, if the first nonmetal has only one, we drop the mono. So this becomes carbon disulfide. And there we go. We have now named all the different types of chemicals. This was a big review. Take your time with it. Pause the video. Try the questions. Play some more. Try them again. Let me know if you have any questions. I hope you guys are all doing well. Take care and all my best.